In the last video, we learned how substances produce light when electrons undergo transitions between electron energy states. In this video, we'll look at different ways light is used. Remember this equation for electromagnetic radiation. It relates energy to frequency to wavelength. This picture shows the energies, frequencies, and wavelengths of the different regions in the electromagnetic spectrum. Let's review how light is produced. Stop the video and fill in those blanks. And the answers are... Remember, this difference in energy corresponds to the wavelength of light emitted. You've used light in many of these different ways. Let's take a look at a few of them. We've all used fluorescent lights before. You turn on the light switch, electricity flows to the bulb, and stop the video and explain how the lamp works. And the answer is, electrical current flows through the electrodes and the energy vaporizes the mercury. Electrons flowing through the electrodes collide with the gaseous mercury atoms with enough energy to form excited state mercury. Electrons in the mercury higher energy electron states undergo a transition down to a lower energy state and releases UV light. That UV light is absorbed by the phosphor coating. Electrons in the excited state phosphor undergo transition to a lower energy state to produce white light. Now, when your fluorescent light burns out, don't throw it away in your trash. The mercury in those lights is very toxic. The green 546.1 nanometer line in the mercury emission spectrum is used to calibrate light detectors. Stop the video and answer these questions. And the answers are: use Avogadro's number to convert from joules per photon to joules per mole. A photon is a particle of light. Substances produce light, but so do chemical reactions. Light can also be used as a reactant in a chemical reaction. Substances produce light in a two-step process. Energy is supplied so an electron undergoes a transition from a lower energy state to a higher energy state. It also works the other way around. Light is supplied to produce energy. That's how a solar cell works. You're going to make a pickle glow in lab. We'll discuss what's happening when you do this experiment. Lasers have many uses. Here are some laser properties and the things that are needed to make a laser work. Rubies are red, and rubies can be used to make a red laser. The red color is due to chromium 3+ ion and alumina. This is a good practice problem, so stop the video and answer these questions. And the answers are: the level 2 to level 1 transition gives ruby its color. The level 1 to level 3 transition occurs when this wavelength of light is absorbed. The level 3 to level 2 transition emits 2550 nanometer infrared light. And these energies should add up. These are the substances that give different gemstones their color. The energy states in a metal ion changes when the mineral is different. Spectroscopy is a study of how light interacts with matter. Stop the video and think, what happens when light comes in contact with a substance? And the answer is, a few things can happen. Two ways a person who studies spectroscopy learns how light interacts with matter is to measure an absorption spectrum or emission spectrum. We looked at an emission spectrum earlier. When an electron in a substance undergoes a transition from a higher energy state to a lower energy state, light is emitted. The wavelength of light corresponds to that difference in energy. In an absorption spectrum, an electron undergoes a transition from a lower energy state to a higher energy state. The wavelength of light absorbed corresponds to that energy difference. The wavelength of light absorbed is not the color you see. The color you see is its complementary color. See the color wheel. So here's the color wheel. The color on the opposite side is its complementary color. For example, the complementary color of yellow is violet. So stop the video and fill in the blanks in these two examples. And the answers are: the green pigment in plants is chlorophyll. There are two types of chlorophyll, chlorophyll A and chlorophyll B. Stop the video and identify the color absorbed by chlorophyll A. And the answer is, chlorophyll A absorbs red, and the complementary color of red is green. That's why chlorophyll appears green. You have two solutions, a dark red solution and a light red solution. Stop the video and answer these questions. And the answers are, you just showed an application of Beer's law, which states that the amount of light absorbed is directly proportional to the concentration of the solution. Do sunglasses absorb or emit light? Now, you're probably not worried about that when you're wearing your sunglasses. Bring a pair of sunglasses to the lab. You're going to do an experiment to see if your sunglasses protect your eyes from UV radiation. Our skin is a good detector of UV radiation. You know that you're exposed to UV because your skin will burn. So sunscreens have chemicals that absorb UV light to protect your skin from UV. This equation shows how SPF is related to the amount of UV light absorbed. And this table relates SPF to the amount of UV absorbed. SPF 20 absorbs 95% of UV light. SPF 30 absorbs 96.7% of UV light. The experts claim you should use at least an SPF 30 sunscreen. Is it worth the extra expense to get a sunscreen with an SPF over 30? You're going to practice applying these principles of light by measuring the spectra of food colors in lab. Wintergreen Lifesavers not only taste like wintergreen, that's from methyl salicylate, they also emit blue-green light when crushed. See practice problem 7. Let's review these ideas of light and color. Stop the video and answer these questions. And the answers are... Good job. Titanium dioxide is the white pigment used in paint and food coloring. It has some interesting properties and applications. This region of the electromagnetic spectrum is used in various types of chemical analysis. We consume a lot of oil, mostly by burning it in a combustion reaction. The products of a combustion reaction, CO2 and water, absorb infrared radiation. These gases trap the heat that would normally go into space and leads to warming of the Earth. The concentration of CO2 is directly proportional to the amount of IR radiation absorbed, according to Beer's law. So the higher the concentration, the more heat that's trapped in our atmosphere. Here are some references if you're interested in greenhouse gases and global warming. This picture shows the absorption spectra of atmospheric gases. Note that CO2 and water absorb in the IR. Oxygen and ozone also absorb in the IR, but also in the UV. These pictures show the Earth's temperature over time. The top graph shows over 1800 years, the bottom graph shows the last 1,000 years. The top graph shows the CO2 concentration over the last 200 years. The bottom graph shows the temperature of the lower atmosphere over the last 200 years. Is there a correlation? 200 years is a long time, but what about over the last 400,000 years? This picture shows what's happening with CO2 and temperature over the last 600 million years. Us humans produce about 6 billion tons of carbon from CO2, but note that from all sources it's 200 billion tons of carbon from CO2. Part of the 6 billion tons comes from respiration. Green plants remove CO2 through photosynthesis. Methane is another greenhouse gas, but is much more potent than CO2. Sheep and cattle produce a lot of methane, but a vaccine will help reduce their emissions. There are a lot of cows in the world, and those cows produce quite a bit of greenhouse gases. A study indicates that the exhaust from a hybrid car is less harmful than the emissions from sheep. Maybe this will slow climate change. This map allows the user to search for greenhouse gas emitters. Although refrigerants are less damaging to the ozone, which protects us from UV, refrigeration uses about 1/6 of all the global energy.